Um, all right. Okay. Welcome everyone to second seminar of Advanced ACC seminar series. We are super excited to have Dr. Brandon Sweeney, who is the Chief Technical Officer at Elect Nano. Dr. Sweeney got his bachelor's in material sciences at RPI and then followed and did his PhD in material science at Texas A&M University. He's worked at the Army Research Labs at the VTWMR Directorate. He has been involved in a couple of startups. He was the VP of Material Development at Essentium, which is a company focused on additive manufacturing. And interestingly, Brandon and I share a little bit of a similar lineage, academic lineage. We both made a stint at the Green Lab. Um, and we are super excited to have him today and talk about the next generation CNT composites. So the floor is yours, Brandon.
All right. Well, thank you so much for having me, Professor Bashith. And it was nice running into you at the airport. Feels like probably about a year ago. And I'm glad that that kind of spun into this opportunity. So thank you for reaching out and hosting me today. Today, we'll be going through some of the technology developments that we've been working on at Elect Nano, really trying to keep it focused on composites, in this case, nanocomposites and their applications in the electronics and semiconductor industries. So I'll be going through a little bit about our company, our core technology and capabilities, some of our technology for how we disperse nanotubes in thermoplastics for injection molding compounds, materials that we do for dispersed nanotubes in capillary underfills that are used in semiconductor encapsulation compounds. Also some work that we've done in silicone functionalized nanotubes for applications in EMI shielding, particularly for 5G communications. And then I have just a few thoughts to share on scaling materials technologies. I think it's just very different than scaling other technology platforms, whether it's software or even hardware. Materials is just a little bit different. And so for anyone who's working in nanocomposites or composites manufacturing, I might have a few words to share on some of the pain that you'll probably experience in trying to scale technologies, but it can also be very rewarding to watch something go from tiny little samples in the lab to much larger scale where it's impacting industry. So I find it incredibly rewarding to work on these kind of applications. And I would strongly suggest that anyone who's working on technologies in the lab or academia, that they keep going with it because it can be very rewarding. All right, so carbon nanotubes. That is primarily what our company works with. And I think everyone by now, after 30 plus years of carbon nanotubes kind of being in the media, in the spotlight, we all have an idea that they're very, very tiny, 10,000 times smaller than a human hair. They're very, very strong on paper, so much higher modulus than steel, higher thermal conductivity, 6 times lighter than steel. And compared to copper, they have much higher conductivity. And so, there's all these great properties of carbon nanotubes that have been discussed. And a lot of this really comes down to, I took a single carbon nanotube and I measured its properties. And so on paper, it looks like if I could just, make that much larger or make a cable out of carbon nanotubes, then surely I'm going to come up with a space elevator, or my plane is going to be 6 times lighter because I threw carbon nanotubes into it. And I think just been very interesting, the last at least 10 years that I've been working in carbon nanotubes. There's little advancements here and there, but I think the danger was when we kind of promised ourselves that this would make everything significantly stronger, significantly lighter. We'd be replacing all the copper in all of our transmission lines with carbon nanotubes. And some of those, may be around the corner. I've seen some really cool advancements in carbon nanotube based wires and stuff. There's a lot more work to do in maturing those technologies. But I think ultimately, carbon nanotubes got a little bit of egg on their face in response to initial claims that were made and some of the challenges that we saw in actually using carbon nanotubes in industry. And so part of the problem is when you take carbon nanotubes that come out of a reactor and you try to work with them, and I kind of did this for many years in Dr. Green's lab, and before that at the Army Research Labs. You'd take a $1,000 bottle of carbon nanotubes at the time, and you'd put it into like an epoxy system, and you'd sonicate it for like a day or a week. And then in some cases, you'd like centrifuge it and try to separate out all the nanotubes that were not dispersed well. And then you're left over with a very dilute solution of maybe a few nanotubes floating around. And then you run to the SEM and you kind of hunt around for that one nanotube that's well bonded to the epoxy, and then you go publish a paper on it. But the reality is, if I really want to scale that up and use it in an industrial relevant way, nanotubes are just really challenging to untangle. The degree of kind of intertwined, bundled, almost like a cotton ball kind of effect that you see in what's coming out of your reactor, it's very challenging to disperse that at scale, especially in high viscosity systems, thermosets and thermoplastics that are relevant for composites. Even if you do manage to get them untangled, nanotubes they're really hard to keep them apart and keep them well dispersed in these systems, because their surface energies are very different typically from the composites that we're trying to put them into. And so I would say the vast majority of literature and many companies that operate in this space have tried to take reactor carbon nanotubes, sonicate or high shear mix them into like a system, and then make a concentrate or dilute it down, study its properties, look at it under a microscope, and then so many times in literature I've seen the conclusions: better dispersion is likely needed in order to fully realize the modulus improvements or the toughness improvements or the electrical properties. It seems to be the repeating mantra of carbon nanotube research that we need better dispersions. And so that's really what our company has focused on. We focused on how do we, at an industrial scale, create better dispersions. I'm not going to say perfect. Perfect is very difficult with carbon nanotubes, but much better dispersions to the point where we're actually kind of tipping the balance of properties in our favor for truly enhancing nanocomposite systems. So at Elect Nano, we have 3 key steps to our technology. Number 1, we clean the carbon nanotubes. So we can start with really any grade of nanotubes to begin with. So we can purchase from a variety of vendors or make our own carbon nanotubes. But number 1, you clean them to remove residual catalysts. Number 2 is our secret sauce, where we debundle the carbon nanotubes in a liquid phase process. I can't go into a ton of detail there. That is what makes our company special. But it's really a way that we've developed to disentangle the carbon nanotubes, separate them out without breaking them into little pieces. So we're not taking a super high power probe sonicator and just beating them to death until they're little tiny chunks of carbon nanotubes. Our company has kind of figured out and patented ways to disentangle the nanotubes gently, but very efficiently. So we kind of matched the process to the type of shear and entanglement that we see in the nanotubes to begin with. Step 3, we functionalize. So after you get the carbon nanotubes separated from each other, to kind of take it all the way across the finish line, you really have to make sure that the nanotubes want to be in the system you're putting them into. And so that involves matching the surface energy and the chemistry of the tubes to that system. And furthermore, you may want to kind of tweak and tune things in order to amplify certain properties and mute others. And I've got a slide on that. We'll talk a little bit more about that. When it comes to the chemistry of the tubes, it is our team's job. We've got a team of chemists that are world-class and have a long background in designing kind of bespoke carbon nanotube functionalization chemistries. And then we've got a team that really specializes in taking those chemistries and scaling them up to very large quantities. But really, it is kind of our job to be the Sherpas as we work with a customer to figure out, here's where they're starting, this is where they want to go, and then how can we kind of link the desired thermoplastic matrix or thermoset adhesive that we're going to put the carbon nanotubes into, and make sure that we have a chemical pathway functionalization route that is economically viable for the application that it's going into, and really make sure that we have a good coupling between the nanotube and the final system. And so I don't intend to go through all of this, but our team has kind of this Sankey plot that we will use and kind of go through in order to figure out a pathway that yields good compatibility. That's also part of our secret sauce. We don't usually disclose the chemistry that we're using for a certain system, but through hundreds and hundreds of experiments and combinations of chemistries and ending points, we have a large library of kind of proven out technology that's sitting on the shelf or out there in the marketplace, and it allows us to kind of rapidly go through and select compatibility. So at the end of the day, what this means is that if you just take regular carbon nanotubes and let's say you sonicate it in epoxy, for instance, you look at it under a microscope and maybe you got it broken up a little bit. You let it sit on a shelf for 30 minutes, an hour, a day, depending on the viscosity of the system. And it's going to look like something on the left here, where the nanotubes are going to reaggregate, form flocks, and they're just really not happy to be in that system. And so when we've done our job right, when we've done all three steps, we go to the picture on the right here, which is the same concentration of carbon nanotubes in an epoxy matrix. And when you look at this under a microscope, it basically looks like a tinted window. It's kind of just a uniformly opaque gray color because we have the nanotubes so well dispersed that even under a microscope, there's really nothing to see in terms of definition of agglomerates or clumps of nanotubes. I've got one other example later in these slides that will kind of also highlight that for capillary underfill materials, but this is the core of what we do. As a company, we've got a long background in developing this technology. There's also other affiliate companies that have kind of utilized this core technology for different applications. So the company with the longest background in this is a company called MRD, Molecular Rebar Design, which kind of developed the initial IP, and that spun out some of these different ventures. MechNano on the additive manufacturing side. MechNano is actually our sister company and focuses all on 3D printing and additive manufacturing. So I've got a few slides on that. There's a company called Black Diamond Structures, which focuses on energy storage materials for batteries, lead acid, and lithium ion. MRD has a lot of work going on in rubbers, which is very exciting for increasing the toughness, wear resistance, rolling resistance of tires. And then there's also a company called Biopact, which is working on drug delivery using discrete carbon nanotube technology. And so all companies kind of share a knowledge basis, and we work together on projects and kind of transfer technology. And that's been one of the really fun things working with all these affiliate companies is watching the interchange of, hey, this worked for this application. We can transfer that over into the electronics world, or things that are working well in our side of things. We can transfer that technology quickly into additive manufacturing and so on. And so it's a really great team that kind of all gels together and kind of works as a team to figure out all the applications for discrete carbon nanotubes across many different industry verticals. And when we work with a customer to kind of find a problem that they're having and how nanotubes might help, we do focus on primarily electrical property enhancements, mechanical properties, thermal, chemical, magnetic, optical. with the different functionalities that we can provide on the carbon nanotubes, we can kind of amplify or mute certain properties. So for instance, there may be an application where we want highly conductive concentrates of carbon nanotubes for ESD protection or EMI shielding. In other applications, we may actually want to functionalize to actually eliminate most of the electrical conductivity in the nanotube because we want an insulating adhesive or encapsulant. We don't want it to conduct electricity, but we do want some of the benefits from fracture toughness improvement. And so we can kind of modify the sidewall of our tube and the starting nanotube that we work with in order to adjust electrical properties. We also usually are working secondarily to make sure that we're not negatively impacting strength and toughness and the modulus of the material. So it's making sure that we're not compromising on physical properties. We've also got one of our team members is an expert in magnetic nanomaterials. And so we can engineer functionalizations into the nanotubes to adjust their magnetic properties, which recently has kind of shown some very interesting applications for advanced processing. With each of these, it really comes down to the application that we're putting the nanotubes into and how can we tailor them for the end goals. I'm going to transition into actually some work that our sister company, MechNano, does. We're co-located here in Phoenix, and MechNano has been working for several years to develop this discrete nanotube technology for additive manufacturing. So we have many commercialized resins that are used across different technology platforms. So these are SLA resins that MechNano has developed. We sell concentrates and also direct photocurable resins. And these are useful primarily for electrical properties. So customers that needed ESD-safe parts. MechNano was the first and leading company to develop ESD-safe SLA resins. And this is challenging because you're using light to cure the material, and carbon nanotubes are typically highly absorptive. So nanotubes absorb from DC to daylight, and so you're kind of battling this. I need to get light into the photocurable system in order to get it to cure, but I also can't have this thing be pure black because that would quench all of my curing energy. And so our team had to work really hard in order to kind of ride the edge of the knife in terms of the process window and material functionalities and grades of nanotubes that we work with to achieve this. But it's absolutely incredible when I see these parts, knowing that their incredible properties are coming from discrete carbon nanotubes that have been put into the system. This is kind of an example of the defunct technology that MechNano uses. And so these are high resolution images of the nanotube dispersion. And so if you just take kind of like off the shelf nanotube powder and you try to like mix it and stir it into SLA resins, you kind of get the image on the right here with lots of ropes and bundles and clumps. And the key to our technology is the ability to disperse and evenly distribute and eliminate the clumps and chunks of carbon nanotubes in these SLA resins. And so when you do that right, you get very consistent electrical properties. Your properties go up, so impact goes up, tensile modulus goes up, tensile strength goes up. And if you do it poorly, if you just take nanotubes and mix it in, you're mixing a bunch of defects in. And you may get some electrical properties, but we see that they're all over the place in terms of the variation in electrical properties. You've got resin rich and carbon nanotube rich areas, and that creates a lot of variation in the electrical properties in the material. And then usually all your mechanical properties go down because you've basically stirred in defects into your component. And especially with SLA, because of the process, if you have areas that are over curing and under curing all over the place, it leads to very non-uniform final properties in your 3D printed parts. We've also developed SLA powders at MechNano, so the ability to basically put our nanotube technology on top of the SLA powders, so you can improve the properties of the system. You get ESD at very low loading levels of carbon nanotubes in this case, And that's a really neat technology for being able to apply it in powder bed processing. And there's several companies that are scaling that technology now, and we commercially offer SLS resins that have our discrete nanotubes kind of built into them. And then finally, on the mech nano side of things, in fused granular fabrication, and then also probably future applications in like FDM printing, we've proven out that our dispersions in thermoplastics can be printed with and provide very uniform electrical properties. And they've been validated on like the Arberg freeformer system in a couple different chemistries now. So I'm going to transition into the elect nano side of things. The key distinction for elect nano is that we do a lot of the same kind of application areas as mech nano, but it's all with traditional manufacturing. So injection molding, semiconductor fabrication operations, jigs, fixtures, and toolings that are machined, anything relating to electronic encapsulants or adhesives, and then even some stuff in like EMI shielding. And so if it has to do with modifying the electrical properties for an electronics and semiconductor applications, and it's not 3D printing, then that's kind of the elect nano world that we live in. And so one of the first applications that we've been working on is media handling trays that are used in semiconductor manufacturing. And so as a computer chip is born, it starts its life off as a wafer, and a wafer, everything in semiconductor is automated. Humans are generally not handling these chips and wafers during the manufacturing process. If a human is touching it, it probably means that it's broken. And so robots and automated equipment handling really is involved in every step of the process. Robots are really neat, but one thing that they really need in order to do their job well is order. You can't just have a random table kind of with parts everywhere, or at least not yet for most robots. They really like things to be ordered and neat and the same every single time. And so when it comes to the wafers, those start their lives off being kind of handled in wafer carriers and FOUPs. And then as they get down the process and they kind of change format from being a wafer to being diced up into dies and chips, they'll continue to live their life during the various parts of packaging in very standardized trays that hold them throughout the rest of their life until they can be packaged in like tape and reel or other packaging formats. And so it's just kind of important because you have to understand that every single computer chip that you interact with, whether it's in your laptop, your phone, your car, your fridge, any computer chip has lived its life in one of these types of fixtures. And probably not just one, probably multiple versions of these as it goes down the process. And so because chip designs are changing all the time and there's different sizes and shapes and formats, there's actually a lot of different varieties of these kind of trays that are used in manufacturing. And so we kind of got involved from a customer that was identifying that the current materials used in these applications were not really meeting requirements for the consistency of electrical properties. And so right now it's very common to use like carbon black or carbon fiber as the additive that imparts the electrical properties to these materials. And so carbon fiber is an amazing material, particularly if you want stiffness. It's really hard to beat carbon fiber from a cost and stiffness standpoint. So I really love it for that. And I love carbon fiber. I used to use it a lot in all of our 3D printing work back in my Centium days. But when it comes to consistency of electrical properties, like if you're a computer chip and you're sitting there in one of these little chip carriers and you've got a 8-micron diameter, millimeter long carbon fiber kind of sitting embedded in a polymer matrix, the way that those carbon fibers align and orient during the injection molding process, it just means that you have a highly conductive fiber and a very insulating matrix, and that's kind of arranged in a random or aligned pattern. And so one of the issues that's kind of cropped up is that on average, the tray may meet the electrical property requirements for surface resistance to be ESD-safe, electrostatic discharge safe. But if you kind of zoom into the scale of the computer chip, it sees areas of overly conductive or like pointy ends of a lightning rod sticking up out of the plastic, or insulating areas between the plastic, or there's areas where the carbon fibers are aligned or randomly oriented. And this can create a lot of variability in the electrical properties. And that's a problem because as chips are put in and out of these things, and as the trays move around or rub against each other, tribo charging and electrostatic charges can build up in these components. And the interesting thing about computer chips is that generally as time goes on, they become more susceptible to ESD damage, not less, because the transistors are continuing to shrink in size. And that means that the amount of voltage that they can withstand before they have a breakdown event actually goes down. And so the next generation of 2 nanometer, 1 nanometer based devices, you're actually going to have to get a lot more intentional about making sure that everything that interacts with these devices on the manufacturing stage is tightly controlled for the electrostatic properties of the material, its surface resistance, volume resistance, to control static charge buildup. And so carbon fiber is not very good at that. And it turns out that carbon nanotubes are excellent at that. But the key is the dispersion component. So before, if you have chunks of carbon nanotubes all over the place, and those chunks are like micron sized, you're kind of back to square one. You've got hot spots, cold spots, and it doesn't really solve the problem. And so a lot of the off-the-shelf carbon nanotube master batches that you can purchase today, it's reactor carbon nanotubes that have been compounded into a thermoplastic, but you look at it under a microscope and it's like Rocky Road ice cream, chunky monkey. You've got chunks of carbon nanotubes that are all over the place. Degree of dispersion is fairly poor. Yes, you'll get some surface resistance that meets requirements, but if you actually are a computer chip, it matters a lot how those nanotubes are distributed throughout the material. And so for a variety of reasons, nanotubes kind of really tip the balance in favor of utilizing the uniformity and the dispersion of discrete nanotubes for these types of applications. And so this is an example of that. This is surface resistance plotted as a function from the injection location in the gate. And so carbon fiber, as it fills the mold cavity, those fibers become oriented or non-oriented, and the way they kind of flow means that their properties go up and down and up and down, and they swing all over the place. When we look at our discrete nanotubes in these same thermoplastic systems, we're like flatlined. We can dial in a specific surface resistance that we want. We don't have to try to average everything out, and we hit it within a single order of magnitude. And so that's really the game-changing opportunity for nanoscale materials, is that they average out all the hot spots and cold spots, and you just get consistent uniform properties throughout the entire component. Now I'm going to switch gears into some of our epoxy applications. In semiconductor manufacturing, once you have your die, one of the next steps is typically to do like a flip chip or multi-die stacking 3D assembly. And so you're basically putting silicon chiplets together and putting it onto a substrate so that you have something that can be encapsulated. And when you do a flip chip process, you'll basically flip it upside down, and you've got solder bumps that connect the chip to the substrate, but there's a gap in between there. There's air in between the solder bumps, and there's a big CTE mismatch, coefficient of thermal expansion mismatch between the die and the substrate. And so that leads to a lot of stresses that build up as these devices thermally cycle. And so the typical way to at least address the issue is to use something called an underfill, where you basically trench and then allow the adhesive to wick underneath the chip and the substrate. So these are high flowability epoxies that are very highly loaded with like silica filler in order to match the CTE between the chip and the substrate. It helps to relieve stresses so that you don't break off your solder bumps during this kind of thermal cycling. The stresses are very high here. And so the fatigue ends up being a really critical component. Fatigue and adhesion of that underfill to the two interfaces dominates the ability of the underfill to do its job well. And so this is kind of like a cross section looking at an underfill. You'll get a capillary edge here, and then the flow of the material underneath that chip. You can see the bumps here. And then if you zoom in, you can see all the little silica particles that are used to tightly pack the rest of the volume so that it has a very low CTE. But you can also see right here on the edge, there's actually a fracture that's starting to form. And so this can start anywhere. You can get a crack on the fillet, and that crack can propagate underneath the device. And then you can either have adhesive or cohesive failure, and the cracks just kind of work their way through the substrate and the die. And if a crack forms, that can let moisture come into the system, or it can allow the stress to build up and catastrophically fail one of your interconnects. And so the next generation of AI chips are no longer, computer chips that are the size of your fingernail. AI chips are gigantic, very, very large chips. In fact, there's a company, I think, up in Seattle or Portland that's making AI chips that are like the entire size of a wafer, like an entire wafer made into a computer chip, which is incredible. But also you have to consider that as all that grows much larger, these problems start to compound in terms of the stresses that build up and having to match all these properties without failing all of your interconnects. And so our technology has started to find applications in improving the fracture toughness of these types of adhesives. And so the first thing that you have to do is figure out how to disperse the nanotubes in these low viscosity epoxies without them becoming unstable. And so if you just take carbon nanotubes, even in this case, discrete nanotubes, and you just try to like sonicate it or blend it into one of these underfill components, at room temperature, it may look like you've got a good dispersion, but these are usually dispensed and cured between 100 and 120 degrees Celsius, and then they'll cure it to its final TG around 160 or 170 degrees Celsius. And so the surface chemistry is changing dramatically throughout that thermal processing. You can't just engineer for stability at room temperature. You have to consider how the surface energy of the entire system is changing over the curing conditions. And so we kind of got excited quickly, and then got not excited quickly when we found out that this is much harder than it looks to get a good nanotube dispersion in a very thin capillary. This is two slides that are spaced out with a single layer of Kapton tape, and you're trying to get it to wick all the way across and not have any played out or wet out of the resin. You want the nanotubes to stay with the system. And so we had to go back to the drawing board with our chemistry team to figure out, how do we solve this? How do we really make sure that the nanotubes are stable in these systems so that we actually can get the reinforcing benefit in the underfill? And so after a lot of work and kind of just brute forcing, figuring out how to get nanotubes dispersed in these types of materials, eventually we came up with a solution, and this is when things are working well. And so I could see this having applications in like resin transfer molding or other carbon fiber layup operations where you're trying to get epoxies to kind of wick and wet out through carbon fiber epoxy or carbon fiber laminate systems because you want the nanotubes to stay with the resin and not just get kind of filtered out or crash out of your epoxy during the curing stage. But this is absolutely critical to realizing the full benefits of fracture toughness improvements, which are generally known for carbon nanotubes. It's probably 20 years ago that the first studies on fracture toughness enhancements were published on carbon nanotubes, but actually doing it well on components that are relevant to the semiconductor industry and composites sectors, it can be more challenging than meets the eye. And so after you do things, quote unquote, the right way, when we were testing K1C and the fatigue fracture performance of these materials, we were happy to discover that compared to control specimens, same formulation, just with silica filler and without nanotubes in them, they typically fail under 1,000 cycles. And with carbon nanotubes added into these systems, we're basically hitting over 5,000 up to 15,000 cycles before the fatigue crack propagates through the material. And so the other thing is the crack growth mechanisms are far more stable. So the more vertical this line is, that means you went from like no crack, no crack, no crack to boom, it failed rapidly. You really want to see that it takes a lot of energy to like open up this crack progressively as energy is expended in breaking your component. And so the nanotubes really kind of arrest the rapid progression of cracks and help to absorb a lot of energy during the actual fracture events. And then what this looks like in terms of fracture surfaces, it like just jumps out at you. The control samples, it's kind of a smooth, glassy surface. The surface roughness kind of matches the diameter of the silica filler that's used. You can see it right, it's kind of hard to see, but right here is your controlled crack area for the plastic deformation zone. And then on the right-hand side, this line right here represents about a 2x increase in the stable crack growth region before it propagates kind of catastrophically. But even then, the surface roughness of the nanotube reinforced system is dramatically higher. And so that's always a good sign when you're looking for a ductile versus brittle failure, is kind of how rough and what's the surface roughness morphology of that fracture surface. So we're really excited about these results. We're working hard to put these into actual computer chips. So coming soon to a phone near you, maybe there will be some nanotubes embedded in the, who knows, iPhone 20 or whatever's coming next. I can't keep track of where Apple is these days. So moving on to the next kind of topic, and I apologize because we were covering a lot of bases here, but I wanted to make sure that we cast a wide net on the various projects our team is working on. EMI shielding. So the name of the game is you've got EMI signals that are all around you. Right now you're being bombarded with Wi-Fi signals and Bluetooth signals. And so the next generation and current generation of electronics rely heavily on controlling EMI absorption, crosstalk interference, meeting FCC requirements. And so there's a need for materials that serve multiple different functions in terms of transferring heat and absorbing stray EMI emissions from components. One of those is thermal gap pads. They're used all over the place in high performance electronics that operate at high frequencies. And then particularly for the next generation of communications in the Ka microwave bands, that's proposed for 5G communications. And it's used for military and satellite communications a lot. But one of the things that we became aware of is that traditional EMI materials like ferrites, they kind of have been designed to work well in our traditional kind of 1 to 10 gigahertz range. But those absorption characteristics of those materials tends to drop off rapidly at higher frequencies, or you can kind of pick one or the other, but you don't have the ability to make a broadband high performance EMI system. Or you can throw in like 30% carbon black or a bunch of like silver flake into stuff. But that can lead to a lot of compromises in terms of mechanical properties, cost. And so for a variety of reasons, we're very confident that our carbon nanotube materials will be able to provide some outstanding benefits for EMI shielding. Back in my Dr. Green days, We had some firsthand experience about how much carbon nanotubes absorb microwave energy, because you could like put a tiny little thing of carbon nanotubes in a microwave oven and you'd put it on for like 2 seconds and it basically explodes. Carbon nanotubes have just a very high intrinsic ability to absorb electromagnetic energy, especially when they're well dispersed and distributed throughout a matrix. And so our team did a lot of functionalizations and optimizing nanotube dispersions in silicones. We used a cool little fixture for measuring the microwave absorption in the Ka bands. It's a 2-port guided free space method for measuring those. I'm not going to kind of go into too much depth, but effectively you use a vector network analyzer, you shoot a wave at it, you have an incident electromagnetic signal. Some of that gets reflected, that's your S11 parameter. Some of it gets transmitted, that's your S21 parameter. And by comparing those signal intensities, the S11 and S21 parameters, you can back out what is your absorption, transmission, and reflection components to the signal. And so when we compare our materials to kind of industry standard EMI absorbers, we can match performance at very low carbon nanotube levels, fractions of a percent up to a few percentage points of carbon nanotubes compared to something that has like 30% silver or ferrites that have been added into it. And then if we supercharge the amount of nanotubes that we put into it, if we do a higher loading level, we're just kind of blowing it out of the water, 80 to 100 decibels, decibel per centimeter in terms of absorption, which is log scaled. So that is a lot of signal quenching. And then when we look at it in comparison to this, basically tells you what component, what fraction of the wave is being absorbed, reflected, or transmitted. This is the control material over here. And so for a very low loading of carbon nanotubes, we're doing better in terms of overall absorption. We're reflecting less of the signal and then transmitting less of the signal. And then if we go to the higher loading levels, again, it's really cool because effectively you're transmitting zero signal, 0.001% of the signal remains transmitted. A lot of it's being absorbed, and then some of it's being reflected. And so this is just really cool because it really just highlights the key benefits of carbon nanotubes to interact with electromagnetic energy at very low loading levels when you have an excellent dispersion and you've kind of achieved percolation in these systems to maximize interactions. So I'll have kind of more updates on that as time goes on, but we're finding a lot of applications where that's useful right now. The last thing I wanted to touch base on before we jump into questions, I wanted to just throw this up here because I've had the opportunity to work with and scale a decent amount of carbon nanotube, in particular nanocomposite materials in additive manufacturing, and now in the electronics and semiconductor industries. And so for anyone that's in academia or in a startup company that's working on particularly materials technologies or material process technologies and composites, just a few things that I've noticed. Scale doesn't necessarily imply bigger. So for instance, in the lab, you may go in and you may take a tip sonicator or a bath sonicator and try to disperse a nanomaterial into an epoxy or a urethane resin. Pick your flavor of material that you're trying to make a composite in. Let's say it's a Maxine that you're putting into an epoxy resin. If you're thinking about well, gee, I did this at the gram scale quantity. I want to start a company that's going to sell Maxine concentrates in epoxy systems. As you're thinking about scale, it doesn't necessarily mean that you take the tip sonicator and then you go rush to the Acme sonicator store and then buy the supersized version of the tip sonicator and just literally like scale your process up bigger. It could, but I would say more often than not, scale a lot of times means that you're going to have to take the lessons learned about the process that was done in the lab phase at the very small scale. You really want to understand, what was the process that yielded a good dispersion that you saw there, and then think about other ways of accomplishing that with tools and process equipment that really lends itself to continuous processing or much larger batch processing technologies. And I would say more often than not, it doesn't mean, just make it larger, or it doesn't mean buy 100 tip sonicators and run this in serial production. I would say that's the exception, not the rule, to really how you would go about increasing throughput for materials-based technologies. So that's one thing that I've seen. A concrete example of that is in the golden days in Dr. Green's lab, we used to take 3D printer filament, and we're trying to put a thin coating on the outside of the filament with carbon nanotubes. So we'd make an ink and we'd dip the filament into it and get a coating on there, but it was an ink that had like chloroform or dichloromethane to dissolve a thermoplastic ink and get it on there. And we'd make like a meter or so at a time. And then when we needed to scale it up, the first thing we did was we made a continuous coating bath, and I ran it up on the side of the Jackie Brown Chemical Engineering building at Texas A&M. So we had this thing going up like 6 stories over a pulley and back down, because that was the only way that we could get the ink to dry out before it touched the pulley and got all wiped off and messed up. And even then, that was really challenging. And so that was kind of, I think, the grad school scrappy way to try to make more filament and scale the process. But in reality, the only way that we actually end up growing that technology at Ascentium was to switch over to an extrusion process. So co-extruding a thin jacket, a sheath on the outside of the filaments. And it made life so much easier, because then you don't have to wait for solvent to dry, and it doesn't mess up the coating. And it has new challenges, but there are much better challenges when your throughput is super high and you can really scale the technology. And so scaling a lot of times means adapting and inventing new ways of accomplishing something at a larger scale. The other thing is bigger can be better. So a lot of times when you're in grad school or in a startup mode and you're trying to do something on the very, very small scale, you're kind of MacGyvering like a setup in order to try to prove out the concept without costing a lot of money in terms of capital equipment. And it leads to a lot of compromises, and your results may be skewed, or you may get very inconsistent batch to batch kind of results in what you're trying to produce. Don't get discouraged about that, I would say, because there are many challenges with scaling process technologies, but one of the cool things is when you can really go bigger, you have a lot of opportunity in order to really control the process and go very quickly, and actually the quality can get better as speeds and throughput go up. And so it takes kind of the like battle hardening of figuring out how to scale a technology, but in the process of doing that, you may actually see a lot of the gremlins and ghosts in a lab scale process go away, because the process lends itself better to being monitored, controlled, and scaled in a consistent, uniform manner. And so don't get discouraged if you're sonicating a nanocomposite and you get 10 different results 10 different times, even though you kind of did it the same way each time. And then the last thing I wanted to say was do what you do best, and then leverage partnerships for all else, especially for startup companies or small and growing technology companies. I think there's at least kind of a misconception that like companies need to be 100% vertically integrated. There's a time and a place for that. I would say typically it's more of your enterprise type companies where vertical integration can lead to a lot of efficiencies in the process and help them at the very large end of scale. But I would say when you're starting out and you're kind of being a lean, mean fighting machine to get traction and developing a new technology, find your core competency and do that really, really well. And then if there's other parts of the process that somebody else is really good at, let them do it. Like I've seen some companies that are trying to like, I don't know, do like fiber placement type layup. And it's like they're inventing their own robot arm or making their own like deposition thing. And I'm like, focus on the technology of the applicator head or the key thing that makes you differentiated. There's a lot of other companies out there that make robot arms, and they can make robot arms really, really, well, and you probably can't. And thinking that you can make a better robot arm is probably a little bit of you'll learn some lessons. And same thing for like manufacturing processes. Like if you can make in our case, we focus a lot on making concentrates or master batches of our materials. That's what we do really, really well. And then we leverage partnerships in order to scale up like compounding, or if we need to make the finished product, you can use toll processors to kind of bridge the gap until you can afford to invest in the CapEx to do that yourself. So if you've got secret sauce and something that's proprietary, keep that close to the chest, do that super well, and then try to leverage other partnerships and relationships in industry to handle other parts of scaling a technology where somebody else may have been doing that for the last 50 or 100 years, and they're outstanding at it. I think you'll go a lot further, a lot faster, and you'll also develop a lot of good friendships and relationships in analogous industries that I think will serve you really well for the rest of your career. And so that is the end of my slides. And I've probably taken too much time because I only left 7 minutes for questions, but I'm sure we might be able to let it run over a little bit. I've got time after this, so I will turn it over for Q&A time.
Yeah, thank you so much, Brandon. This was great. We have a bunch of questions, so maybe we can start going through them. Just for all the participants, you should be able to unmute yourself now. So let's go from the top. Leo, if you want to unmute yourself and ask your question, please feel free. Or I guess I can start. So Leo has a question. How much does your dispersion chemistry on the CNTs decrease your CNT and macro composite performances relative to unmodified CNTs? I presume that covalent bonding disrupts CNT intrinsic properties and non-covalent bonding could shield dispersed effects of CNTs.
Yeah, and it really depends on the final applications. You're exactly right that what and how much you do to the sidewall of the tubes can affect finished properties. And so, for instance, in the like EMI applications, our goal is to maintain as much of the intrinsic conductivity of the tube as possible. There's also some cool things that our company has figured out in terms of covalent or non-covalent bonding that actually helps to promote percolation. And so like when two nanotubes are near each other, there's kind of tunneling junction resistance between the two. And there's some situations where you can actually kind of link those up intentionally in order to promote lower junction resistance. And so I would say that modifying the sidewall of the tubes doesn't always decrease electrical properties.
Mm-hmm.
Same thing with mechanical properties. We focus a lot on the interface around the tube. And so there's some situations where a direct covalent linkage, for instance, with epoxies, you may pick a direct covalent linkage that maximizes stress transfer in more of a, I would call stiff way. And that's going to maximize things like your stiffness, elastic modulus, but that may actually decrease the toughness of the system at high strain rates because the ability to absorb energy in that very stiff bond doesn't allow energy to be released in a controlled manner. And so in cases where we're trying to maximize the fracture toughness or fatigue toughness, we may actually engineer a softer interface in between the nanotube and the matrix so that there's a little bit of give there. Again, it's a balance because we're trying not to modify or decrease the elastic modulus or the TG of the system, but you can actually get in there and tailor the hardness or softness of the interface between the tube and the matrix in order to achieve a certain end property.
Very interesting. Yeah, and actually you can use that for fatigue as well. If you can have the stick slip mechanism for CNTs to improve your fatigue performance. Great. Next, I think Dr. Green, if you want to unmute yourself and ask your
I
question.
can ask on behalf of Dr. Green and everyone.
Sure. Yeah.
Brandon, Dr. Green's question was, can the methods of functionalization that you've used be used for other chemistries of carbon nanomaterials or CNTs?
Yeah, absolutely. I think that anything that is kind of SP2, SP3, kind of graphitic in nature would lend itself well to our process. So carbon black, that's a challenge to disperse. Graphene, graphitic nanoparticles certainly would be applicable.
Okay, thank you.
Mhm.
And next question that I had was, so have you tested the EMI shielding of these materials in other bands like the X band at lower frequencies?
Yeah, so we have some data that suggests that the absorption mechanism is dominated by the electrical properties of the system. And so we can model kind of the gaps in between, but we do have X band, and I've got from like a couple kilohertz up to several megahertz. And then we have some like X band results. It's very linear in the sense that the response is not going to be like, oh, a peak where there's resonance, or it's not going to drop off heavily. Nanotubes, once you have a percolated system, it really depends on kind of the density of the system. At higher frequencies, there can be some, I would call them weird interactions in terms of multiple internal reflections and different kind of the domains of how bundled or dispersed the nanotubes are. And so, but when you have a very good dispersion, there shouldn't be as many weird anomalies as if you had like a conductive network plus a whole lot of chunks everywhere, because that can cause some, I would say, non-linearities in your electromagnetic response.
Okay, thank you.
And I think the next question actually alludes to the same point. I know Troy might have dropped out, but I can ask the question. I can imagine for stealth application, you would rather have no reflection rather than no transmission. Would change in your functionalization help with this?
Yeah, and typically you would want to get a little bit more clever in terms of how you engineer that interface. And so with stealth applications, I wouldn't want to go too deep into it, but you have an incident electromagnetic wave. Even if that hits a perfect dielectric, some of it's going to get bounced back because you've got basically the propagation in free space is not going to match when you change dielectric constants. And so the name of the game usually with stealth applications is you want to match the dielectric constant of air or whatever medium it's going to be in as closely as possible, and then have a continuous gradient where you're transitioning slowly into kind of your highly or maximum absorption kind of chunk of material. And so gradients, or kind of, I would call them strange, like weird structured kind of domains of carbon nanotubes can be very interesting in those applications. I don't want to go into a whole lot more detail, but if you have more questions, you can contact us and we can go through applications in stealth or radar absorption. But you have to get clever when you're trying to maximize that, because a homogeneous uniform material with a single set of electrical properties is never going to be the optimum for maximizing absorption.
Interesting. Very interesting. Sayam, if next question is by Sayam. Sayam, I don't know if you want to unmute yourself and ask the question.
Hi, Brandon. Thanks for the great seminar. I just had one question. So basically, the uniform dispersion of CNTs which you observed, is that purely a matrix-based property, which is an interaction with the functionalized CNTs, or are you using some surfactants or processing conditions in order to achieve a good dispersion?
I mean, number one, it's starting off with well-dispersed carbon nanotubes, and then the secondary component to achieve the consistent dispersion it involves sidewall modification. Our team also, we sometimes will use more than one method. So we use non-covalent and covalent methods to maximize absorption. So sometimes when we're trying to balance properties, we'll do some partial covalent functionalization, but we don't try to quote unquote decorate the sidewall to maximum kind of modification. We might only kind of lightly modify the sidewall of the tube to get an initial surface energy match. And then we may switch over to a non-covalent like polymer wrapping or block copolymer dispersant type systems in order to take over the rest of the way in order to balance between destroying the electrical properties of the tube and maximizing compatibility. And it really depends on the application. So we use both. I can't really go into a whole lot more details of exactly how we do that, but we absolutely do use every tool at our disposal for getting across the finish line in a commercial application.
So I guess the name of the game is like, how do you tailor that interface to get like the desired properties? Okay, great.
Yeah, and so like for the underfill application, that was tricky because a single type of functionalization was not appropriate. You could either get stability at room temperature, or we could engineer for stability at high temperature, but it was really hard to get both. And so in that situation, we used a dual functionality to try to split the difference between stability across the entire change in the viscosity and surface energy of that underfill matrix throughout the entire process window.
Interesting. We'll move to the next question. Khalid, if you want to unmute yourself and ask your question, please. I'll tag team with Khalid and I'll ask his question. So this question is, have you tried using this technology for surface modification to enhance adhesion of thermoplastic fibers to thermoplastic matrix? That's very, that's
I
a
haven't.
very interesting.
That's
yeah,
very
that's
specific. I'm guessing this is like a self-reinforced polymer, maybe, or perhaps
like Kevlar
PBI or Kevlar, something like that. Yeah. No, we haven't. I would say in those situations, it's a bit different surface chemistry. I would say a lot of our background and expertise is in graphitic type surface modifications. It's possible that there could be some kind of transfer maybe in highly aromatic rigid rod type polymer systems where some of the same like pi interactions might overlap, but I have not tried that. And again, if you've got some interest there and specific use cases, you can contact us on our website. I think my email, I'll make sure the email is somewhere in the follow-up, but you can always reach out to us if you want to chat about a specific use case.
Yeah. We have one question from Huang She. If you want to unmute. Yep.
Sure. This is Huaishan from Green Group. So I have a question about the EMI shielding applications. So when you design your CNT in the polymer matrix for the EMI shielding application, have you looked at the orientation or distribution of CNTs in the matrix, or is just randomly distributed?
The results that I shared were randomly distributed,
Okay.
but kind of going back to the stealth applications, or I would call it kind of the more sophisticated EMI applications, orientation or multi-layer structures would absolutely come into play. So for instance, like if you're designing a gap pad absorber, you may want to, that sits against a chip, you may want to have something that maximizes absorption in a thicker layer, and then have kind of a backing, like a thinner backing, where you've increased the nanotube loading in order to maximize the total attenuation coefficient of that layer, And so what might happen is if you have an incident electromagnetic signal, it goes through your absorbing layer, and you quench 30 dB of signal. It hits the highly reflecting layer that can be much thinner because it doesn't take as much thickness in order to achieve that degree of attenuation. The signal actually gets bounced backwards back through your absorbing layer, and so you kind of get like a doubling of your absorption through a intelligently designed multi-layer system. And you can even do that in many layers. So there's other weird things like Salisbury screens and multi-layer structures that microwave engineers use. In my opinion, microwave engineers are like a step away from black arts magicians because the things that they deal with are just so wacky. And all of electrical engineering goes out the window when you start talking about microwaves and free space wave propagation. It's just a very different world. So those are some of the tricks that you might use, and certainly orienting through an electric field or magnetic field, orienting the nanotubes could be another strategy for inducing such gradients or intentionally designing a very specific kind of absorbing structure.
Cool. Thank you.
Yeah. Great. I think that takes care of all the questions. So thank you again, Brandon, for such a wonderful seminar. And we'll surely keep on bugging you with more questions in the future. This is really, really cool technology, and super excited to see all the cool things that you do in the future.
Yeah, again, thank you for having me. It's been great to share technology, and just next time we connect, we'll dive into some of the stuff that you've been working on, because I think you're also headed in a pretty cool direction with composite systems. So thank you.
Yeah, thank you so much. Take care.